The prehistoric world experienced weather that often changed the environment and affected the survival of plants and animals. Long before humans existed, Earth went through powerful volcanic winters, extreme heat, long droughts, severe storms, freezing ice ages, and massive floods. These events changed forests into deserts, caused sea levels to rise and fall, and forced many species to adapt, move to new areas, or become extinct. However, some weather events lasted for only a few years, while others continued for thousands or even millions of years, changing Earth's climate over long periods. So what made the weather terrifying? The Archean and early Proterozoic eras were two of the longest periods in Earth's early history. During these times, the planet was very different from the world that exists today. The land, oceans, air, and climate were all changing as Earth slowly developed into a place that could support a wider variety of life. One of the most important features of these early eras was the warm climate. Earth remained much hotter than it is today for a very long time. This heat came from many different sources, including the young planet's interior, the movement of molten rock, frequent volcanic activity, and the slow cooling of the crust. These conditions affected every part of the planet and shaped the development of the atmosphere, oceans, continents, and the earliest living organisms. The Archean era began about 4 billion years ago and lasted until about 2.5 billion years ago. The early Proterozoic era followed and continued until about 1.6 billion years ago. During both eras, Earth was still going through major changes. Although solid land and oceans already existed, the planet remained active. Volcanoes erupted often, the crust moved constantly, and new rock formed across many parts of the surface. Heat from deep inside Earth escaped through cracks, volcanic vents, and areas where the crust was thin. This steady release of heat helped keep the planet warm over long periods. The inside of Earth contained much more heat during these early eras than it does today. Some of this heat came from the energy left over from the planet's formation. As Earth formed from countless pieces of rock and metal coming together, enormous amounts of energy were released. Much of this energy became trapped inside the growing planet. Even after hundreds of millions of years, a large amount of this heat still remained beneath the surface. Another source of heat came from radioactive elements inside Earth's rocks. As these elements slowly broke down, they released energy that warmed the interior. Since there were larger amounts of some radioactive elements during the early history of Earth, this process produced more heat than it does today. The hot interior caused the mantle to move more actively. The mantle is a thick layer of hot rock beneath Earth's crust. Although this rock is solid, it can slowly flow over very long periods. As hotter material rose and cooler material sank, the mantle carried heat toward the surface. These movements affected the crust above and caused frequent volcanic eruptions. Fresh magma reached the surface through cracks and volcanoes, forming new rock and releasing gases into the atmosphere. Volcanoes played a major role in shaping the climate. Every eruption released large amounts of water vapor, carbon dioxide, sulfur gases, and other substances into the air. Water vapor later cooled and became part of the oceans, while carbon dioxide remained in the atmosphere. Carbon dioxide trapped heat from the sun and helped keep Earth's surface warm. Without enough carbon dioxide, the planet could have become much colder, because the young sun gave off less energy than it does today. Scientists have found strong evidence that the young sun was less bright during the Archean era. It produced less heat and light than it does today. Even though the sun was weaker, Earth did not become completely frozen. Geological evidence shows that liquid water existed over much of the planet during this time. Ancient rocks that formed in oceans contain signs that water remained in a liquid state for long periods. This means another source of warmth helped balance the weaker sunlight. Greenhouse gases in the atmosphere provided much of this warming. Carbon dioxide was one of the most important greenhouse gases during these early eras. Large volcanic eruptions added carbon dioxide to the atmosphere over millions of years. Since there were very few living organisms to remove this gas from the air, much of it remained in the atmosphere. Plants that exist today remove carbon dioxide through photosynthesis. But during most of the Archean era, there were no forests, grasses, or flowering plants. Only tiny microorganisms existed, and their influence on the atmosphere was still limited during the earliest part of Earth's history. Methane may also have helped warm the planet. Some ancient microorganisms produced methane as part of their normal life processes. Methane is a powerful greenhouse gas that traps heat very effectively. Even if methane was present in smaller amounts than carbon dioxide, it may still have played an important part in keeping Earth's surface warm enough for liquid oceans. Scientists continue to study how much methane existed during these early eras, but many believe it contributed to the overall climate. The atmosphere during the Archean era looked very different from today's atmosphere. Oxygen was almost completely absent. Instead, gases such as carbon dioxide, nitrogen, water vapor, methane, and small amounts of hydrogen and ammonia were more common. The lack of oxygen affected many chemical reactions taking place on Earth's surface. Rocks weathered differently, minerals formed under different conditions, and the atmosphere itself behaved differently from the one that surrounds Earth today. Clouds formed as water evaporated from the warm oceans and later condensed in the cooler parts of the atmosphere. Rain fell regularly and returned water to the oceans and land. This continuous movement of water formed an active water cycle. Rivers carried broken rock and minerals into the seas, where layers of sediment slowly collected. Over millions of years, these sediments hardened into sedimentary rocks that still preserve valuable information about Earth's early climate. The oceans themselves were warmer than many oceans today. Heat from the atmosphere, the hot interior, and underwater volcanic activity all contributed to warmer seawater. Hot water circulated through cracks in the ocean floor where magma heated it from below. These hydrothermal systems released minerals into the oceans and created environments rich in dissolved chemicals. Many scientists think such places provided suitable conditions for some of the earliest forms of life. The ocean floor looked very different from the modern seafloor. New crust formed rapidly because Earth's hotter interior caused faster movement of tectonic plates. Old crust sank back into the mantle after relatively short periods. This constant recycling of oceanic crust changed the shape of ocean basins and affected ocean circulation. Warm water moved through these changing basins, carrying heat and dissolved minerals across large areas. The continents during the Archean era were much smaller than those of today. Instead of large, stable continents covering wide regions, there were many smaller pieces of crust rising above sea level. These early landmasses slowly grew as volcanic islands collided and joined together. Granite-rich rocks became more common as Earth's crust developed greater stability. Over time, these smaller land areas expanded into larger continental blocks. The small size of the continents influenced the climate in several ways. Large areas of ocean covered Earth's surface, allowing water to absorb and store heat. Warm oceans released water vapor into the atmosphere, supporting regular rainfall. Coastal regions changed often as sea levels rose and fell, and as tectonic activity reshaped the landscape. Volcanic islands appeared in many parts of the oceans. Some remained active for long periods, while others became inactive and slowly eroded. Fresh lava flows covered older rocks, creating new land surfaces. Rain and waves gradually broke these rocks into smaller pieces, adding sediments to nearby seas. This continuous cycle of volcanic building and erosion shaped much of Earth's surface during the Archean era. Earth's crust was thinner in many places than it is today. The hotter mantle below transferred heat more easily through the thinner crust. As a result, volcanic activity remained widespread. Large amounts of molten rock reached the surface through volcanic eruptions and long cracks in the crust. These events added fresh material to the continents and ocean floor, while releasing additional gases into the atmosphere. Meteorite impacts also continued during the early Archean, although they became less common over time. Large impacts released enormous amounts of energy when rocks from space struck Earth's surface. These collisions temporarily heated local areas, melted rock and sometimes vaporized water. Dust and gases entered the atmosphere after major impacts, affecting local and regional conditions. As the number of impacts slowly decreased, volcanic activity became the main force driving changes at Earth's surface. Life during the Archean era consisted entirely of microscopic organisms. These tiny forms of life lived mainly in the oceans, where water protected them from intense ultraviolet radiation reaching the surface. Without a protective ozone layer, harmful radiation from the sun reached Earth's surface much more easily than it does today. Water provided some protection, allowing microorganisms to survive beneath the surface of lakes and oceans. Some microorganisms obtained energy directly from chemicals released by volcanic activity. Others used sunlight to produce food. Early forms of photosynthesis gradually became more widespread during the later part of the Archean era. These organisms slowly began producing oxygen as a waste product. At first, this oxygen reacted immediately with dissolved iron and other substances in the oceans instead of building up in the atmosphere. Large amounts of dissolved iron existed in the warm oceans. When oxygen produced by microorganisms mixed with seawater, it combined with the iron to form iron-rich minerals. These minerals settled to the ocean floor and formed thick layers that later became banded iron formations. These rock layers provide important evidence for the gradual increase of oxygen during Earth's early history. As oxygen production continued over many millions of years, more oxygen became available after much of the dissolved iron had reacted. Eventually, oxygen slowly began entering the atmosphere in greater amounts during the early Proterozoic era. This major environmental change affected Earth's climate, chemistry, and living organisms. Although oxygen levels remained much lower than modern levels, the increase marked one of the most important developments in the planet's history. The rise of oxygen also affected methane in the atmosphere. Oxygen reacted with methane, reducing the amount that remained in the air. Since methane trapped heat efficiently, its decline may have reduced part of the greenhouse warming that had helped keep Earth warm for such a long time. Scientists continue to study how strongly this process affected global temperatures during the early Proterozoic era. Snowball Earth was one of the most extreme periods in the long history of Earth. During this time, almost the entire surface of the planet became covered with ice. Thick glaciers spread across continents, while frozen seas reached from the polar regions towards the equator. Many scientists believe that only small areas of open water remained, if any at all. This was a time when Earth looked very different from the world that exists today. The familiar forests, grasslands, deserts, and warm oceans of the modern planet did not yet exist. Instead, Much of the surface was covered by snow and ice that reflected sunlight back into space and helped keep the planet cold. This frozen period happened during a very distant part of Earth's history. Long before animals, dinosaurs, birds, or flowering plants appeared. It took place during the Neo-Proterozoic era. Scientists believe that there were at least two major periods when Earth entered this frozen condition. One happened around 720 million years ago, while another occurred around 635 million years ago. These events lasted for millions of years and changed the planet in important ways. The idea that Earth could have become almost completely frozen was difficult for many scientists to accept when it was first suggested. Today, a large amount of geological evidence supports the idea that the planet experienced these severe ice ages. Even though researchers continue to debate exactly how much of Earth was covered by ice, most agree that these frozen periods were among the coldest episodes in the history of the planet. Scientists discovered clues to these ancient events by studying rocks found on different continents. These rocks contain signs that glaciers once moved across areas that are now warm tropical regions. Some rocks have long scratches cut into their surfaces. These marks were made when large pieces of stone trapped beneath moving glaciers scraped against solid rock. The scratches remained preserved after the ice melted and later became buried beneath newer layers of sediment. Other rocks contain large pieces of stone that appear to have been dropped into fine sediments. These rocks are called drop stones. They formed when rocks carried by floating ice became trapped inside icebergs. As the ice slowly melted, the stones fell into soft mud on the sea floor. Over time, the mud hardened into rock while the larger stones remained inside it. These unusual rock formations provide strong evidence that floating ice once existed over ancient oceans. Scientists also study rocks called tillites. These rocks formed from sediments left behind directly by glaciers. Tillites contain a mixture of clay, sand, gravel, and large stones that glaciers pushed together while moving across the land. The discovery of tillites in places that were once close to the equator suggests that ice reached regions that today are known for warm temperatures. The position of continents during this period played an important part in the development of snowball Earth. Hundreds of millions of years before these frozen episodes, Earth's continents were arranged differently from today. Many landmasses were located near the equator. Warm temperatures and heavy rainfall caused rocks in these tropical regions to break down through a process known as weathering. Rainwater mixed with carbon dioxide from the atmosphere to form weak acids that slowly dissolved minerals in rocks. As weathering continued, carbon dioxide was removed from the atmosphere and carried into rivers and oceans. There it became locked inside minerals and sediments. Since carbon dioxide is a gas that helps keep Earth's surface warm by trapping heat, removing large amounts of it caused the atmosphere to lose some of its warming ability. As carbon dioxide levels slowly fell, global temperatures gradually became lower. The cooling process did not happen quickly. It took millions of years for enough carbon dioxide to be removed from the atmosphere. During this time, glaciers slowly expanded from high mountain regions and the poles. As more snow remained on the ground throughout the year, the bright white surface reflected more sunlight back into space. Less solar energy was absorbed by Earth's surface, allowing temperatures to fall even further. This process created a powerful cycle. More cooling produced more snow and ice. More snow and ice reflected even more sunlight. As additional sunlight was reflected away, temperatures continued to decrease. Scientists call this process the ice albedo feedback. It became one of the strongest forces driving the planet toward widespread freezing. Eventually, glaciers spread farther from the poles. Ice sheets became thicker and covered huge areas of land. Sea ice expanded across the oceans. Once the frozen surface reached lower latitudes, the cooling process became even stronger, because regions near the equator normally receive the greatest amount of sunlight. Covering these areas with reflective ice greatly reduced the amount of heat absorbed by the planet. Many climate models suggest that once ice reached a certain distance from the poles, Earth entered a condition that became difficult to reverse. The growing ice reflected so much sunlight. The temperatures continued falling until nearly the entire planet became frozen. Oceans developed thick layers of sea ice. Some estimates suggest that sea ice may have reached a thickness of hundreds of meters in certain places, although thickness likely varied depending on local conditions. The atmosphere during Snowball Earth was very different from today's atmosphere. Carbon dioxide levels had become much lower before the freezing began. Clouds still formed, but the cold temperatures limited the amount of water vapor in the air. Since water vapor is also a greenhouse gas, lower amounts reduced Earth's ability to retain heat. This added to the cooling effect. The oceans changed dramatically during this frozen period. Thick ice covered much of the ocean surface. Wind could no longer mix surface waters with deeper waters as effectively because the ice acted as a barrier. Exchange between the atmosphere and the ocean became much weaker. Oxygen levels in deeper waters may have decreased in many places because fresh oxygen could not easily reach them. Sunlight could not pass through thick ice very well. Only limited amounts of light reached the water beneath the ice sheets. This affected organisms that depended on sunlight to produce food through photosynthesis. Many forms of microscopic life had to survive under difficult conditions. Some may have lived beneath thinner ice, while others remained in places where cracks allowed light to enter the water. Scientists believe that some life survived in small environments where conditions remained suitable. Areas near volcanic activity may have provided liquid water because heat from Earth's interior prevented complete freezing. Hot springs on land and hydrothermal vents on the ocean floor likely remained active throughout the frozen period. These places released heat and minerals that supported communities of microscopic organisms. Some coastal regions may also have contained patches of open water during certain seasons or in areas where ocean currents remained active. Even if the oceans were almost completely frozen, these small refuges could have allowed life to continue. Tiny organisms living in sediments beneath the ice may also have survived because the ocean floor remained warmer than the frozen surface. Life on Earth during Snowball Earth was still relatively simple. There were no large land animals or forests. Most living things were microscopic organisms such as bacteria and algae. Early forms of more complex organisms had also begun to appear before these frozen events. These living things faced enormous challenges as temperatures fell and habitats disappeared beneath expanding ice. Some microorganisms were able to survive by entering inactive states during harsh conditions. Others continued growing slowly in cold water beneath the ice. Certain bacteria can live without sunlight by using chemical energy from minerals released through volcanic activity. These organisms may have played an important role in maintaining life while the planet remained frozen. Evidence from fossils suggests that life did not disappear during Snowball Earth. Instead, it survived in scattered environments that remained suitable for living organisms. After the ice retreated, these surviving populations spread into newly available habitats and continued evolving. Volcanoes remained active throughout the frozen period, even though the surface was covered by ice. Deep beneath Earth's crust, molten rock continued moving upward. Volcanic eruptions released gases into the atmosphere, including carbon dioxide. Normally, weathering removes carbon dioxide from the atmosphere, but during Snowball Earth much of the land was buried beneath thick ice. Rainwater had little contact with exposed rocks, so weathering slowed greatly. Since weathering became much weaker, volcanic carbon dioxide slowly accumulated in the atmosphere over millions of years. Although each eruption released only part of the total amount needed, continuous volcanic activity gradually increased atmospheric carbon dioxide levels. The greenhouse effect slowly became stronger. As carbon dioxide continued increasing, Earth's atmosphere trapped more heat. Eventually, enough greenhouse gases accumulated to begin warming the planet despite the highly reflective ice. Once melting started, dark ocean water and exposed land absorbed much more sunlight than snow and ice. This reduced the amount of sunlight reflected back into space. The warming process then accelerated. Melting ice exposed larger areas of dark surfaces that absorbed even more heat. Rising temperatures caused additional melting. This warming feedback worked in the opposite direction from the earlier cooling process. Large rivers formed as glaciers melted. Huge amounts of fresh water flowed into the oceans. Sea levels changed as the ice disappeared. Sediments washed from the land into coastal waters. Rivers carried dissolved minerals that had accumulated during the long frozen period. Scientists have found unusual layers of rock called cap carbonates, directly above glacial deposits from Snowball Earth. These carbonate rocks formed rapidly after the glaciers melted. Their appearance in many parts of the world suggests that dramatic environmental changes occurred during the transition from frozen conditions to a much warmer climate. The formation of cap carbonates may have resulted from the rapid weathering of rocks exposed after the ice melted. High levels of carbon dioxide in the atmosphere produced heavy rainfall containing dissolved carbon dioxide. This rain reacted with rocks, carrying large amounts of dissolved minerals into the oceans. Carbonate minerals then formed thick deposits on the seafloor. The oceans experienced major chemical changes as melting continued. Fresh water from glaciers mixed with salt water. Nutrients washed into the oceans from newly exposed land. These nutrients supported the growth of microscopic organisms. Increased biological activity may have changed oxygen levels and affected marine ecosystems. Scientists also study changes in carbon isotopes preserved inside ancient rocks. Different biological and geological processes leave distinctive patterns in carbon isotopes. Rocks formed before, during, and after Snowball Earth show unusual isotope signals that match major disruptions in Earth's carbon cycle. These chemical records provide valuable evidence that the planet experienced extraordinary environmental changes. There are still questions about exactly how completely Earth froze. Some scientists support the classic Snowball Earth model, in which nearly all oceans became covered with thick ice. Others support a related idea known as Slushball Earth. In this model, much of the planet became frozen, but areas of open water remained near the equator. These open regions could have made it easier for photosynthetic organisms to survive. Research continues because the geological evidence can often be interpreted in different ways. Computer climate models are constantly improved as scientists learn more about ancient atmospheric conditions, continental positions, ocean circulation, and solar brightness. Each new discovery helps refine our understanding of these remarkable events. The Sun itself was slightly less bright during the time of Snowball Earth than it is today. Even though the difference was not extremely large, it reduced the amount of energy reaching Earth. This made the planet somewhat more vulnerable to cooling if greenhouse gas levels became low enough. Earth's continents continued moving during these frozen periods because tectonic plates never stopped shifting. Mountain building, volcanic eruptions, earthquakes, and seafloor spreading continued beneath the frozen surface. These geological processes slowly reshaped the planet even while glaciers covered much of its surface. Glaciers themselves became powerful geological forces. As they moved under their own weight, they scraped away rocks, carved valleys, transported sediments, and reshaped landscapes. Huge amounts of crushed rock accumulated beneath the ice sheets. When melting finally began, these sediments were carried into rivers, lakes, and oceans. Strong winds likely swept across the frozen landscape. Large ice-covered regions contained little vegetation because complex land plants had not yet evolved. Wind easily lifted fine dust from exposed areas and carried it across long distances. Some of this dust settled onto glaciers and eventually became trapped within ice layers. Seasonal changes probably still occurred even though Earth remained extremely cold. Regions near the equator continued receiving more sunlight than the poles during the course of the year. However, thick ice prevented large seasonal warming in many places. Temperatures remained below freezing across vast areas throughout the year. The thickness of continental ice sheets varied from place to place depending on snowfall, temperature, and local geography. In mountain regions, glaciers flowed through valleys toward lower elevations. On flatter land, enormous ice sheets spread outward in all directions under their own weight. Sea ice differed from continental glaciers because it formed directly from frozen ocean water. Snow falling on top of sea ice added thickness over time. Pressure caused some layers of ice to deform slowly. Cracks opened and closed as winds and ocean movements shifted the frozen surface. Ocean circulation slowed beneath widespread sea ice. Normally, differences in temperature and salt content help move enormous volumes of water around the world. Thick ice reduced contact between the atmosphere and the ocean, affecting these circulation patterns. This influenced the transport of heat, oxygen, and nutrients. The atmosphere likely contained higher levels of dust during certain stages of snowball Earth. Dry conditions in exposed regions allowed fine particles to become airborne. Dust settling onto ice slightly darkened its surface in some places, allowing it to absorb a little more sunlight. Although this effect was relatively small, it may have influenced local melting. Scientists continue examining ancient minerals for evidence about temperatures during snowball Earth. Certain minerals form only under specific environmental conditions. By studying these minerals together with chemical signatures and fossil evidence, researchers reconstruct ancient climates with increasing accuracy. Radiometric dating allows scientists to determine the ages of rocks associated with snowball Earth. Radioactive elements naturally decay into other elements at known rates. Measuring these changes provides estimates for when ancient rocks formed. This technique helps place glacial deposits within Earth's long geological timeline. Magnetic minerals preserved in rocks provide additional information. When sediments formed long ago, tiny magnetic grains aligned themselves with Earth's magnetic field. These preserved directions allow scientists to estimate the latitude where the rocks originally formed. Discovering glacial rocks that formed near the equator strongly supports the idea that ice spread into tropical regions. Snowball Earth influenced Earth's carbon cycle, water cycle, and chemical cycles in lasting ways. Long periods of freezing interrupted many normal environmental processes. Weathering slowed, river systems changed, and ocean chemistry shifted. When melting occurred, these systems became active again, producing rapid environmental changes. The frozen world also affected the evolution of life. Although conditions became extremely difficult, surviving organisms adapted to cold, darkness, and limited food supplies. After the glaciers disappeared, new environments became available across the planet. Fresh coastlines, shallow seas, and nutrient-rich waters supported expanding populations of microorganisms and early complex life. Researchers continue investigating whether environmental changes following Snowball Earth helped create conditions that supported the later appearance of increasingly complex multicellular organisms. Improved oxygen levels, changing nutrient supplies, and altered ecosystems may all have contributed to later biological developments, although many details remain under study. Snowball Earth remains one of the most remarkable chapters in Earth's geological history, because it demonstrates that the planet's climate can undergo enormous changes over very long periods. The evidence preserved in rocks across many continents shows that glaciers once reached regions that are now warm, while volcanic activity, atmospheric chemistry, and geological processes eventually returned Earth to a warmer state. The study of these ancient frozen worlds continues to improve scientific understanding of climate systems, geological change, ocean chemistry, atmospheric evolution, and the long history of life on Earth. Billions of years ago, Earth was a very different planet from the one that exists today. The shape of the continents, the size of the oceans, the thickness of the atmosphere, the amount of heat coming from the planet's interior, and the movement of the air all created weather systems that often behaved in ways that would seem unfamiliar today. Among the most powerful parts of this ancient weather were the enormous storms that formed over the vast oceans covering much of Earth's surface. These storms were part of the natural movement of heat, water, and air. They helped shape coastlines, affected the chemistry of the oceans, carried water across great distances, and influenced the conditions in which life developed and spread. During the earliest part of Earth's history, the planet was still cooling after its formation. Heat escaped from deep inside the planet much faster than it does today because the young Earth contained much more internal energy left over from its formation and from the decay of radioactive elements. Volcanoes released large amounts of gases into the atmosphere, including water vapor, carbon dioxide, nitrogen, sulfur compounds, and many other gases. As Earth continued to cool, water vapor slowly changed into liquid water and began falling as rain. This rainfall lasted for a very long time, filling large low areas and creating the first oceans. The earliest oceans covered much of Earth's surface. The first continents were small and scattered, leaving enormous stretches of open water. These huge oceans played a major role in controlling weather. Water absorbed heat from the sun during the day and released it gradually over time. Warm water heated the air above it, causing the air to rise. Cooler air then moved into the empty space left behind. This continuous movement of warm and cool air created winds that travelled across great distances over the oceans. As sunlight reached Earth's surface, some parts of the oceans became warmer than others. Areas closer to the equator received more direct sunlight throughout the year. The water in these regions became much warmer than water closer to the poles. This uneven heating created strong differences in temperature across the planet. Warm air rising above tropical oceans met cooler air moving from higher latitudes. These differences supplied energy for large weather systems. The atmosphere of the ancient Earth was also different from today's atmosphere. Early in Earth's history, there was little or no free oxygen. Instead, nitrogen and carbon dioxide formed much of the atmosphere, along with water vapor and smaller amounts of methane, ammonia, sulfur gases, and other volcanic gases. Water vapor was especially important because it carried large amounts of heat. As warm air rose, the water vapor cooled and changed into tiny droplets, forming clouds. During this process, heat stored in the water vapor was released into the atmosphere, giving storms additional energy. Over the wide ancient oceans, clouds often grew into enormous systems. Warm ocean water supplied a continuous flow of moisture into the air. Rising air carried this moisture higher into the atmosphere, where it cooled and condensed into thick clouds. As long as warm water continued feeding the storm, it could keep growing larger and stronger. The largest storms may have lasted for many days, as they travelled across open water with very little interruption. The ancient oceans provided almost unlimited space for storms to develop. Modern oceans are divided by continents of different sizes, but many periods of Earth's history had fewer land barriers. Some ancient oceans stretched across much of the planet without large continents, blocking the movement of air or ocean currents. Storms forming over these waters could travel for thousands of kilometers while continuing to draw moisture from the sea beneath them. Ocean temperatures strongly influenced the strength of storms. During many periods in Earth's history, global temperatures were warmer than today. Warm oceans caused faster evaporation. Large amounts of water entered the atmosphere every day. This constant supply of moisture made it easier for large storm systems to form. Warm water also allowed storms to maintain their strength for longer periods because the ocean continued providing heat and moisture. Earth rotated rapidly throughout much of its history. The planet's rotation affected the movement of air through the Coriolis effect. This caused winds to curve rather than move in straight lines. Curving winds allowed storms to develop rotating patterns. Once rotation began, storms could organize into large circular systems. Strong rotating storms were able to gather warm, moist air from broad areas of the ocean. The exact speed of Earth's rotation changed slowly over billions of years. Early in Earth's history, the day was shorter than it is now because the planet rotated faster. A shorter day meant that the atmosphere experienced stronger effects from Earth's rotation. This may have influenced the paths taken by ancient storms and affected the way air circulated around the planet. The young sun also affected ancient weather. Early in Earth's history, the sun produced less energy than it does today. Even so, Earth's atmosphere contained gases that trapped heat efficiently, allowing liquid water to remain on the surface. This combination of sunlight and greenhouse gases created conditions in which storms continued forming over the oceans despite the sun's lower brightness. Volcanic activity added another important influence. Ancient Earth experienced frequent volcanic eruptions, especially during its earliest billions of years. Volcanoes released huge amounts of gases and tiny particles into the atmosphere. Water vapor from eruptions increased the amount of moisture available for clouds. Sulfur gases sometimes formed tiny particles that acted as surfaces where water droplets could gather. This process helped clouds develop. Large volcanic eruptions could temporarily cool parts of the atmosphere by reflecting some sunlight back into space. After these eruptions, temperature differences between different regions could change, altering wind patterns and storm formation. As volcanic dust slowly settled out of the atmosphere, weather patterns shifted again. Lightning was common within many ancient storms. As ice particles, water droplets, and strong winds moved inside towering clouds, electrical charges built up. Eventually, these charges became so great that lightning flashed between clouds or between clouds and the surface below. Lightning released enormous amounts of energy in a very short time. Some scientists believe lightning played an important role in the chemistry of early Earth. Electrical energy passing through the atmosphere could break apart simple gases and allow them to form more complex molecules. Some of these molecules may have become part of the chemical processes that eventually led to the appearance of life. Heavy rainfall accompanied many ancient storms. Warm air carrying large amounts of moisture produced thick clouds capable of releasing tremendous amounts of rain. Rivers flowing from the first continents carried minerals into the oceans. Rain also weathered rocks, slowly breaking them apart and transporting tiny particles downhill into lakes and seas. The first coastlines were constantly changing under the force of powerful storms. Strong waves crashed against rocky shores, breaking rocks into smaller pieces. Loose sediment was carried away by waves and currents before being deposited elsewhere. Over long periods, repeated storms reshaped coastlines many times. Wind blowing across the ocean created waves that travelled long distances. During especially powerful storms, waves became extremely large. These waves stirred the upper layers of the ocean, mixing warm surface water with cooler water below. This mixing distributed heat and nutrients through the water. Ocean mixing was important for living organisms after life appeared. Nutrients from deeper water reached the surface where tiny organisms could use them. Surface water carrying oxygen and sunlight also mixed downward. This circulation supported many forms of marine life as they evolved over time. Storm-driven currents carried sediments far from land. Tiny grains of sand, mud, volcanic ash, and organic material settled onto the ocean floor. Over millions of years, these layers hardened into sedimentary rocks. Today, geologists study these rocks to learn about ancient climates, storms, ocean chemistry, and the history of Earth's surface. During the Archean Eon, which began about 4 billion years ago and ended about 2.5 billion years ago, Earth's continents remained relatively small. Much of the surface consisted of open ocean. Storms likely formed over these broad waters on a regular basis. Although direct evidence is limited because very old rocks are rare, scientists study surviving rock formations to understand these ancient environments. Clouds over the early oceans were probably very thick in many places because evaporation remained active over warm water. Large cloud systems reflected some sunlight while trapping heat beneath them. Their movement influenced rainfall patterns across the oceans and the small land areas that existed. Air pressure also affected storm development. Differences in air pressure caused winds to flow from high-pressure areas toward low-pressure areas. As warm air rose above heated oceans, low-pressure regions formed. Air rushed inward to replace the rising air. This movement helped organize large storms and strengthened wind speeds. Some storms may have developed into enormous rotating systems, similar in structure to tropical cyclones. Warm ocean water, moist air, and Earth's rotation provided the basic ingredients needed for these storms. Without large landmasses interrupting their movement, some storms may have survived much longer than many modern tropical systems. The ancient oceans themselves were not exactly like those of today. Early seawater contained different amounts of dissolved minerals because rivers, volcanoes, and underwater hydrothermal systems continuously added chemicals. The salt content may also have differed during various periods of Earth's history. These differences affected water density, ocean circulation, and the movement of heat. Hydrothermal vents on the ocean floor released hot water rich in dissolved minerals. These underwater systems heated nearby seawater and created local circulation patterns. Although their influence remained much smaller than the energy supplied by sunlight, they contributed to the overall movement of ocean water. The moon also influenced ancient oceans. Tidal forces caused water levels to rise and fall. Early in Earth's history, the moon orbited closer to Earth than it does today. This created stronger tides in many places. Tidal currents mixed seawater, moved sediments, and interacted with storm-driven waves to produce constantly changing coastal environments. When storms occurred during periods of especially high tides, coastal flooding became more extensive. Water reached farther inland, carrying sand, mud, shells, and other materials before flowing back toward the sea. Repeated flooding gradually built new coastal deposits. As Earth's continents slowly grew larger through volcanic activity and plate movement, weather patterns became more complex. Mountains forced moist air upward, causing additional rainfall. Valleys guided winds in certain directions. Coastlines created areas where land and sea temperatures differed, encouraging local storms. During the Proterozoic Eon, beginning about 2.5 billion years ago, oxygen slowly accumulated in the atmosphere after photosynthetic microorganisms released it as a byproduct. This change gradually altered atmospheric chemistry. Different gases affected the movement of heat through the atmosphere, influencing climate and storm behavior. Storms remained important during periods when Earth experienced global glaciations. Large parts of the planet became covered by ice during several episodes, often called snowball Earth events. Even during these cold times, storms continued moving moisture through the atmosphere. Snowfall, ice formation, and freezing rain became major parts of the water cycle in many regions. When ice eventually melted, after these glacial periods, huge amounts of fresh water entered the oceans. Ocean circulation changed as fresh water mixed with salty seawater. These changes affected climate and the development of new weather systems over the oceans. During warmer intervals between major glaciations, storms once again drew energy from warm seas. Rainfall increased in many places. Rivers became active, transporting large amounts of sediment into coastal waters. Ocean currents redistributed this material across broad regions. As multicellular life evolved, storms influenced marine ecosystems in many ways. Strong waves mixed nutrients into shallow water, supporting the growth of microscopic organisms that formed the base of marine food webs. Storms also transported larvae and tiny living organisms from one region to another, helping species spread across the oceans. Large storms affected the oxygen content of seawater by mixing surface water with deeper layers. Surface water gained oxygen through contact with the atmosphere and through photosynthesis by tiny organisms. Mixing carried this oxygen downward, where it supported animals living below the surface. Storms sometimes damaged shallow marine habitats. Powerful waves disturbed sediments on the seafloor, burying some organisms while exposing others. Coral-like reefs that developed later in Earth's history occasionally suffered damage from repeated storm activity, although they often recovered over time. The supercontinent cycles that occurred throughout Earth's history influenced ocean size and storm behavior. When continents joined together into large landmasses, enormous oceans surrounded them. These broad oceans allowed storms to travel over long distances without interruption. When continents separated again, new coastlines and smaller ocean basins developed, changing wind patterns and storm tracks. During the time of the supercontinent Pangaea, one enormous ocean called Panthalassa covered much of Earth's surface. Warm tropical waters, changing wind systems and seasonal heating likely supported large storms across this immense body of water. The central regions of the supercontinent experienced very different weather because they lay far from the ocean's moisture. Storms over ancient oceans also influenced the carbon cycle. Rain dissolved carbon dioxide from the atmosphere before reaching Earth's surface. Rivers carried dissolved materials into the oceans, where marine organisms later used some of the carbon to build shells and skeletons. After these organisms died, some of this material settled onto the seafloor. Storm-driven waves helped break apart coastal rocks, increasing weathering. Weathering released minerals that rivers transported into the sea. These minerals became nutrients for marine organisms and also participated in chemical reactions affecting ocean composition. The atmosphere and oceans constantly exchanged heat. Warm water heated the air above it, while cooler air cooled the ocean surface. Storms greatly increased this exchange because strong winds mixed the air and water more effectively than calm conditions. This process helped spread heat around the planet. Cloud cover influenced temperatures over the oceans. Thick clouds blocked some incoming sunlight, while also trapping heat leaving Earth's surface. The balance between these effects depended on cloud type, thickness, altitude, and time of day. Ancient storms therefore affected both local and global temperatures. Scientists study ancient storms using several types of evidence preserved in rocks. Layers of sandstone may record strong wave action. Ripple marks preserved in sediment show the movement of water. Mud cracks, fossil remains, chemical signatures, and mineral deposits all provide clues about ancient weather conditions. Some rock layers contain evidence of giant waves produced during severe storms. These waves moved large amounts of sand into deeper water, leaving distinctive patterns that remain visible after hundreds of millions of years. Careful study of these structures helps scientists estimate the strength of ancient storms. Computer models also help researchers understand prehistoric weather. Scientists combine information about ancient continents, ocean temperatures, atmospheric gases, solar energy, and Earth's rotation. These models calculate how air and water would likely have moved under different conditions. While no model can reproduce every detail perfectly, they provide valuable information about possible storm behavior. Ancient storms varied from season to season. As Earth traveled around the Sun, different parts of the planet received changing amounts of sunlight. Seasonal heating altered wind directions and rainfall patterns. Even on the early Earth, these seasonal changes affected where storms formed and how they moved. Ocean currents carried warm water toward cooler regions and cooler water toward warmer regions. These currents changed the distribution of heat across Earth's surface. Storms interacted continuously with these currents. Strong winds sometimes strengthened surface currents, while ocean temperatures influenced the intensity of storms. The development of sea ice during colder periods affected storm activity. Ice covered parts of the ocean, reducing evaporation from those areas. Storms therefore depended more heavily on open water regions where moisture remained available. Changes in sea ice coverage altered atmospheric circulation over large distances. Dust carried by strong winds sometimes traveled far across the oceans before settling into the water. This dust contained minerals such as iron and phosphorus that served as nutrients for microscopic marine life. Storms therefore helped deliver important materials from land into distant parts of the ocean. The interaction between storms and ocean biology became increasingly important as life became more diverse. Algae growing near the ocean surface responded to changing sunlight, nutrient levels, and water mixing caused by storms. Their growth affected oxygen production and the removal of carbon dioxide from the atmosphere. Storms also influenced the movement of floating organic material. Dead plants, microorganisms, and other natural debris drifted across the sea under the action of winds and waves. Some eventually sank to the seafloor, where they became part of sediment, layers that preserved valuable information about ancient environments. The strength of storms differed across geological time because Earth's climate changed repeatedly. long periods of warmth alternated with colder intervals. Atmospheric composition evolved as volcanic activity, biological processes and chemical reactions changed the balance of gases. Each of these changes influenced how much energy became available for storms. Some ancient storms likely produced rainfall lasting many hours or even several days. Rivers overflowed into surrounding lowlands. Fresh water mixed with seawater in coastal environments, changing local salinity and affecting marine organisms living near river mouths. Wind speeds during the strongest storms may have reached very high levels, creating rough seas across enormous areas. Large waves generated by these winds travelled away from the storms that created them, reaching distant coastlines long after the main weather system had moved elsewhere. Thunder echoed through many ancient storm clouds as lightning repeatedly discharged electrical energy. Nitrogen in the atmosphere reacted during these powerful electrical events, forming compounds that later entered the soil and oceans through rainfall. These compounds became part of Earth's natural chemical cycles. Even after forests evolved much later in Earth's history, storms continued shaping the oceans through river systems. Rain falling over land washed leaves, soil, and nutrients into streams. Rivers carried this material into coastal waters, where storms distributed it farther across the sea. Throughout Earth's long history, gigantic storms over ancient oceans remained part of the continuous circulation of water, heat, and air. They formed because sunlight warmed the oceans, evaporation filled the atmosphere with moisture, rising air created clouds, Earth's rotation organized winds into rotating systems, and temperature differences supplied energy that allowed these vast storms to develop across the immense waters covering much of the planet. Acid rain and toxic skies were important parts of some of the most dangerous volcanic events in Earth's long history. These events happened many millions and even billions of years before human beings appeared. During these times, the planet experienced periods when enormous volcanoes released huge amounts of gas, ash, dust, and molten rock onto the surface. Some eruptions lasted for only a short time, but others continued on and off for thousands or even millions of years. These long periods of volcanic activity changed the air, the land, the oceans, and the climate. They also affected almost every living thing that existed at the time. Volcanoes have always been part of Earth's natural system. They formed because the inside of Earth has remained extremely hot since the planet was created. Heat deep beneath the surface melts rocks and creates magma. This magma rises through cracks in Earth's crust because it is less dense than the surrounding solid rock. When the pressure becomes great enough, the magma reaches the surface and erupts as lava, volcanic ash, and gases. Every volcanic eruption releases different amounts of material depending on the size of the volcano, the type of magma, and the amount of pressure trapped underground. Small eruptions can affect only nearby areas, but giant volcanic events can influence regions thousands of kilometers away. Some of the largest eruptions in Earth's history released enough material to cover vast areas with thick layers of lava. These events created enormous volcanic regions known today as large igneous provinces. They were formed when massive amounts of magma flowed out through long cracks instead of a single volcanic mountain. Instead of one explosion, lava continued pouring onto the surface again and again over very long periods. Each new flow covered older rocks, creating thick layers that sometimes reached several kilometers in total thickness. Along with lava, volcanoes released huge amounts of gases into the atmosphere. Water vapor was usually the most common gas. Carbon dioxide was another major gas released during eruptions. Volcanoes also released sulfur dioxide, hydrogen sulfide, hydrogen chloride, hydrogen fluoride, carbon monoxide, and many other gases in smaller amounts. Although some of these gases were released naturally throughout Earth's history, the greatest volcanic events produced amounts that were much larger than normal. Sulfur dioxide became one of the most important gases during these ancient eruptions because it played a major role in the formation of acid rain. After entering the atmosphere, sulfur dioxide mixed with oxygen and water vapor. Chemical reactions slowly changed the gas into sulfuric acid. Tiny droplets containing this acid formed inside clouds. When rain fell from these clouds, it carried the acid down to Earth's surface. This process created acid rain that spread across large regions. Hydrogen chloride released by volcanoes also mixed with water in the atmosphere. This formed hydrochloric acid, which became another source of acidic rainfall. Hydrogen fluoride could also dissolve into water droplets and produce harmful acidic solutions. Together, these chemicals made rainfall much more acidic than ordinary rain. The stronger the volcanic activity became, the greater the amount of acidic material entering the atmosphere. The atmosphere during these periods often looked very different from the clear blue skies seen today. Thick clouds of volcanic ash spread through the air after major eruptions. Fine particles remained suspended high above Earth's surface for long periods because they were extremely small and light. Winds carried them across continents and oceans. In some places the sky became dark even during daytime because sunlight struggled to pass through the thick layers of ash and dust. Ash itself was made of tiny pieces of volcanic glass, minerals, and rock fragments. Although the particles were small, they could still damage living tissues. Plants became covered with ash, reducing their ability to carry out photosynthesis. Leaves blocked by ash received less sunlight, making it harder for plants to produce the food they needed for growth. Thick layers of ash also buried forests, grasslands, wetlands, and other environments where many forms of life lived. The combination of ash and acidic rainfall placed enormous stress on ancient ecosystems. Acid rain damaged leaves, stems, roots, and young plant tissues. Acidic water flowing into the soil changed the chemical balance underground. Important nutrients that plants needed for healthy growth were washed away more easily. At the same time, harmful metals trapped inside rocks became dissolved in the acidic water. These metals entered streams, rivers, lakes, and eventually the oceans, where they affected aquatic life. Many soils became less fertile after repeated exposure to acid rain. Some plants could survive these harsh conditions better than others, but many species experienced slower growth or widespread death. Forests near active volcanic regions were especially vulnerable because they received the greatest amounts of acidic rainfall and volcanic ash. Trees weakened by acid damage became more likely to die from disease, insects, or continuing environmental stress. Ancient rivers carried acidic water away from volcanic regions into larger bodies of water. Lakes often became more acidic, making survival difficult for many freshwater organisms. Fish, small aquatic animals, algae, and tiny microorganisms all depended on suitable chemical conditions. When acidity increased beyond their limits, many populations declined. Food chains became unstable because the disappearance of one group of organisms affected many others that depended upon them. The oceans also received large amounts of volcanic material. Rivers transported dissolved chemicals into coastal waters. Volcanic ash settled directly onto the ocean surface, where waves mixed it into seawater. Sulfur compounds, metals, and other substances spread through marine environments. Some nutrients released by volcanic ash encouraged rapid growth of microscopic marine organisms. These sudden increases sometimes used up large amounts of oxygen when the organisms died and decomposed. Areas with very low oxygen became difficult places for many marine animals to survive. The skies above active volcanic regions contained not only acidic gases, but also enormous amounts of smoke-like particles known as aerosols. These tiny particles reflected part of the sunlight that normally reached Earth's surface. As a result, temperatures sometimes dropped for periods after very large eruptions. The cooling could last from months to several years after individual eruptions. During prolonged volcanic episodes lasting thousands of years, repeated eruptions continually added fresh aerosols into the atmosphere, making climate conditions highly unstable. While sulfur aerosols often caused cooling, carbon dioxide released by volcanoes produced a different effect over much longer periods. Carbon dioxide remained in the atmosphere much longer than volcanic ash or sulfur aerosols. As its concentration slowly increased, it trapped more heat near Earth's surface. This gradual warming sometimes continued long after the skies had become clearer. Ancient volcanic events therefore affected climate in several stages, with cooling during periods of heavy ash release, followed by longer periods of warming as carbon dioxide accumulated. Many ancient volcanic provinces produced repeated eruptions instead of one single event. Each eruption added more gases and ash to the atmosphere before the effects of earlier eruptions had completely disappeared. This continuous cycle placed increasing pressure on Earth's natural systems. Forests damaged by one period of acid rain had little opportunity to recover before another wave of acidic rainfall arrived. Lakes and rivers remained chemically stressed for long periods. Animal populations already weakened by changing food supplies faced additional environmental challenges. The effects of toxic skies reached far beyond the immediate volcanic region because winds transported gases around much of the planet. High-altitude air currents carried sulfur dioxide, ash, and other volcanic materials across great distances. Areas located far from the volcanoes sometimes experienced acidic rainfall, even though no volcanic mountain stood nearby. Tiny particles eventually settled onto land and into oceans across wide regions. During parts of Earth's early history, volcanic activity was much more common than it is today. The young planet contained greater amounts of internal heat, leading to more frequent movement of magma toward the surface. The atmosphere during these distant times also differed greatly from the modern atmosphere. Oxygen levels were much lower for long periods, while volcanic gases played a much larger role in determining atmospheric chemistry. As volcanic eruptions continued, they helped shape the composition of the air that surrounded the planet. Over immense spans of time, natural processes slowly removed many volcanic gases, while other geological and biological processes added new gases, gradually changing the atmosphere into the one that later supported increasingly complex forms of life. Extreme droughts have happened many times during the long history of Earth. They are not only part of the modern world, they also shaped the ancient planet long before humans appeared. Some of the most severe dry periods happened during prehistoric times when large parts of the land received very little rainfall for thousands or even millions of years. During these long dry periods, rivers became smaller or disappeared, lakes dried up, plants struggled to survive, and many animals had to move to new places in search of food and water. These changes affected almost every living thing on Earth. They also changed the land itself, creating vast deserts that stretched across enormous areas. A drought happens when an area receives much less rain than normal for a long time. A short drought may last for only a few months or several years, but prehistoric droughts often lasted much longer. They continued through many generations of plants and animals. Some lasted because of changes in the atmosphere, while others were caused by changes in ocean currents, movements of the continents, volcanic activity, mountain building, and slow changes in Earth's orbit around the Sun. Since these changes often happened very slowly, the dry conditions also developed over long periods. The early Earth looked very different from the planet that exists today. The continents were not in their present locations. They slowly moved across the surface of the planet because of plate tectonics. As the continents moved, they changed the paths of winds and ocean currents. These changes affected where rain could fall. Some regions became wetter, while others became much drier. Areas that once supported forests slowly turned into open plains, rocky landscapes, and sandy deserts. The atmosphere also changed over Earth's history. The amount of carbon dioxide, oxygen, methane, and water vapor changed many times. These gases influenced temperatures across the planet. Higher temperatures increased the rate at which water evaporated from oceans, lakes, rivers, and soil. If enough moisture did not return as rainfall, the land became drier year after year. Plants lost access to water, and the ground became hard and dusty. Cloud formation depends on moisture in the atmosphere. When warm air rises, cools, and forms clouds, rain may fall if enough water droplets gather together. During many prehistoric droughts, weather patterns prevented enough moist air from reaching certain regions. Winds carried moisture away or blocked rain clouds from entering dry areas. As a result, clear skies remained for long periods, allowing strong sunlight to heat the ground every day. Mountain ranges also played an important part in creating dry environments. When moist air reaches a mountain range, it rises along the slopes. As the air rises, it cools and releases rain on one side of the mountains. After crossing the peaks, the air becomes much drier. This creates a rain shadow where very little rain falls on the other side of the mountains. Ancient mountain ranges created many large dry regions in prehistoric times, helping deserts expand over wide areas. The arrangement of continents had a strong influence on rainfall. When land masses joined together into giant supercontinents, large inland regions formed far away from the oceans. Moist ocean air could not easily travel such long distances. By the time it reached the center of these huge continents, most of its moisture had already fallen as rain near the coasts. The inland regions remained dry for very long periods. This happened several times during Earth's history as different supercontinents formed and later broke apart. One of the best-known supercontinents was Pangaea. During the late Paleozoic era and the early Mesozoic era, nearly all of Earth's major land areas were joined together into one enormous continent. The interior of Pangaea was located very far from the oceans. Because of this great distance, rainfall became very limited in many central regions. Large deserts formed across vast areas. Wind carried loose sand across the landscape and built enormous sand dunes that sometimes stretched beyond the horizon. Evidence of these ancient deserts still exists today. Rocks that were once loose desert sand have hardened into sandstone over millions of years. These sandstone formations preserve the shapes of ancient dunes. Scientists study the direction of layers inside these rocks to learn which way the wind blew in the distant past. These rock layers show that powerful winds shaped many prehistoric deserts over very long periods. Dry climates also affected rivers. Rivers depend on rainfall, melting snow, or underground water. During long droughts, rivers carried less water. Some rivers became seasonal, flowing only during short wet periods. Others disappeared completely, leaving behind dry channels filled with sand and gravel. These abandoned riverbeds can still be found in ancient rocks, showing where water once flowed across landscapes that later became deserts. Lakes were also greatly affected by prolonged drought. As rainfall decreased, lake levels slowly fell. Smaller lakes dried up first, while larger lakes gradually shrank over thousands of years. As water evaporated, minerals dissolved in the water became more concentrated. Eventually, these minerals formed thick layers of salt, gypsum, and other evaporate rocks on the lake floor. Today, these mineral deposits provide important evidence that dry climates existed in the past. Groundwater became increasingly important during long droughts. Water stored beneath the surface often remained available after rivers and lakes disappeared. Plant roots grew deeper in search of moisture, while animals depended on springs that reached underground water. As droughts continued, groundwater levels also declined. Springs stopped flowing, making survival even more difficult for living organisms. Plants developed many ways to survive dry conditions. Some grew deep roots that reached underground water. Others produced small leaves to reduce water loss. Thick outer coverings helped keep moisture inside stems and leaves. Some plants completed their entire life cycle during short, rainy periods before the land became dry again. Seeds often remained buried in the soil until rain returned, allowing new plants to grow after long dry intervals. Ancient forests often disappeared as drought spread across the land. Trees need large amounts of water to survive. During extended dry periods, many forests became thinner as older trees died. Grasslands replaced forests in some regions because grasses generally require less water than large trees. If drought continued, even grasslands could disappear, leaving only scattered shrubs and hardy plants adapted to desert conditions. The disappearance of forests changed local climates. Trees release water vapor into the atmosphere through their leaves. This process adds moisture to the air and can help support rainfall. When forests declined, less moisture entered the atmosphere. This often made already dry conditions even drier, creating a cycle that encouraged deserts to continue expanding. Wildfires became more common during dry climates. Dead plants and dry vegetation easily caught fire after lightning strikes. Fires spread rapidly across dry grasslands and forests. Although some plants recovered after fires, repeated burning made it harder for forests to return. Open landscapes gradually replaced wooded regions, increasing the size of dry environments. Animals faced many challenges during prehistoric droughts. Large plant-eating animals depended on fresh vegetation and reliable water sources. As plants became scarce, these animals traveled greater distances searching for food. Some populations became smaller because fewer young animals survived. Others migrated into wetter regions where water and plants remained available. Plant-eating animals influenced meat-eating animals. Predators depended on healthy populations of prey. As herbivores moved away or declined in number, predators also had to travel farther to find food. Competition increased among hunters living in shrinking areas where water remained available. Many animals gathered around rivers, lakes, and springs, making these places important centers of prehistoric life. Smaller animals often survived drought better than larger animals. Many could hide underground in cool burrows where temperatures remained lower and moisture lasted longer. Some became active only during cooler parts of the day or at night, reducing water loss caused by heat. Others stored food during wetter seasons before dry conditions returned. Reptiles generally handled dry climates better than many amphibians because their skin reduced water loss. Amphibians depended heavily on moist environments for breeding and survival. As wetlands disappeared during long droughts, many amphibian populations declined or disappeared from dry regions altogether. Insects also responded to changing climates. Some species survived by laying eggs that remained dormant until rain returned. Others migrated to wetter environments. Insects played important roles in prehistoric ecosystems by pollinating plants, breaking down dead material, and serving as food for many animals. Changes in insect populations affected entire food webs. Microorganisms living in the soil also experienced changes during prolonged drought. Bacteria and fungi help break down dead plants and animals, returning nutrients to the soil. Dry conditions slowed many of these processes because microorganisms require moisture to remain active. As a result, nutrient cycling became less efficient in many drought-affected regions. The soil itself changed as drought continued. Without enough plant cover, wind easily picked up loose particles and carried them away. This process, known as wind erosion, removed fertile topsoil that had taken many years to develop. The remaining ground became less able to support plant growth. Strong winds also transported dust across great distances, sometimes covering nearby regions with fine layers of sediment. Sand dunes became one of the most visible features of expanding prehistoric deserts. Wind pushed loose grains of sand across the ground. As the sand collected, dunes slowly formed. Their shapes changed depending on wind direction, wind strength, and the amount of available sand. Some dunes remained in place for long periods, while others slowly moved across the landscape. Dust storms became frequent in dry environments. Fine particles lifted high into the atmosphere and traveled hundreds or even thousands of kilometers before settling again. These dust clouds affected sunlight reaching the surface and influenced weather patterns in surrounding regions. Layers of ancient wind-blown dust preserved in rocks provide important evidence of prehistoric dry climates. Changes in sea level sometimes influenced drought. During periods when sea levels fell, larger areas of land became exposed. This changed coastlines and affected the movement of moist air from the oceans. Inland regions often became even farther from the sea, reducing the amount of rainfall reaching those areas. Ocean temperatures also influenced rainfall. Warm ocean water increases evaporation, adding moisture to the atmosphere. Cold ocean water reduces evaporation. Changes in ocean circulation sometimes cooled or warmed large areas of the oceans, changing where rain clouds formed. Regions that lost their regular supply of moist air often entered long periods of drought. Earth's orbit around the Sun changes slightly over very long periods. The shape of the orbit, the angle of Earth's axis, and the direction in which the axis points all change slowly through natural cycles. These slow changes affect how sunlight reaches different parts of the planet. They influence temperatures, seasons, rainfall, and the strength of winds. Over many thousands of years, these natural cycles contributed to periods of wetter or drier climates. Volcanic activity also affected prehistoric droughts in different ways. Large volcanic eruptions release gases and tiny particles into the atmosphere. Some eruptions temporarily cooled the planet by blocking part of the sunlight. Others released large amounts of carbon dioxide over long periods, contributing to warmer climates. These changes influenced rainfall patterns in different parts of the world. Massive volcanic provinces formed when enormous amounts of lava covered huge areas of land. These volcanic events sometimes continued for very long periods. The gases released during these eruptions changed atmospheric conditions and affected global climate. Some scientists believe that these events contributed to severe droughts during several periods of Earth's history. The Permian period experienced extensive dry climates across many parts of Pangaea. Large deserts spread across the interior of the supercontinent. Seasonal rainfall became limited in many regions, while temperatures remained high during much of the year. Fossil evidence shows that many plants and animals adapted to these difficult conditions, although others disappeared from the driest areas. The Triassic period also experienced widespread arid conditions. Much of the interior of Pangaea remained dry because the continent still covered an enormous area. Rivers often flowed only during certain seasons, while many lakes became temporary. Red sandstones and evaporite deposits formed under these dry conditions and remain visible today in many parts of the world. During the Jurassic period, the gradual breakup of Pangaea slowly changed weather patterns. New coastlines formed as continents separated. Moist ocean air reached some areas that had previously been dry. Certain deserts became smaller, while new dry regions developed elsewhere because changing geography altered the movement of winds and rainfall. The Cretaceous period generally had a warmer global climate. Although many areas received abundant rainfall, some inland regions still experienced prolonged drought. Seasonal dry periods remained common in certain parts of the world. Fossil plants and ancient soils show evidence of repeated cycles of wet and dry conditions. Even before Pangaea formed, earlier supercontinents also experienced extensive dry environments. Whenever large continents developed, inland areas usually became drier because of their distance from the oceans. This repeated pattern appears many times throughout Earth's geological history. Scientists study ancient droughts using many different types of evidence. Sedimentary rocks preserve information about the environments in which they formed. Sandstone often indicates ancient deserts, while mudstone may record rivers, lakes, or floodplains. Salt deposits suggest that water bodies evaporated under hot, dry conditions. Each type of rock provides clues about prehistoric climates. Fossils also help scientists understand ancient droughts. Certain plants grow only under dry conditions, while others require abundant water. Fossil leaves, wood, roots, pollen, and spores reveal the types of vegetation that once covered different regions. Animal fossils also provide evidence because different species preferred different climates. Ancient soils, known as paleosols, preserve signs of long-term weather conditions. Some ancient soils contain minerals that form only in dry climates. Others show cracks caused by repeated drying. These features allow scientists to estimate how much rainfall an area may have received millions of years ago. Tree rings provide valuable information about drought during more recent parts of Earth's history. Each ring usually represents 1 year of growth. Narrow rings often indicate dry years, while wider rings suggest wetter conditions. Although trees do not extend back to the oldest prehistoric periods, younger fossil forests preserve valuable climate records. Chemical studies also reveal information about ancient rainfall. Different forms of oxygen, carbon, and other elements become more or less common under different climate conditions. Scientists examine these chemical patterns in rocks, shells, and fossils to estimate temperatures and rainfall from the distant past. Wind direction preserved in sand dunes also provides evidence about ancient climates. The slopes inside sandstone layers formed as wind pushed sand across the desert surface. Measuring these layers allows scientists to determine the prevailing wind directions that existed millions of years ago. Satellite technology has made it easier to identify ancient desert landscapes. Images taken from space reveal patterns that are difficult to recognize from the ground. Ancient river channels buried beneath sand, old dune fields, and dry lake basins become visible through detailed mapping techniques. Desert expansion often happened gradually rather than suddenly. Rainfall slowly became less reliable, rivers became smaller, vegetation declined, wind erosion increased, sand covered more land each year. Over many thousands of years, landscapes that once supported rich ecosystems slowly transformed into deserts. Not every dry period affected the entire planet at the same time. While some regions experienced severe drought, other areas remained wet. Global climate systems constantly shifted as continents moved, mountains rose, oceans changed, and atmospheric conditions evolved. This created a changing pattern of dry and wet regions across Earth's surface. Many prehistoric deserts were much larger than deserts found today. Some covered millions of square kilometers across the interiors of ancient continents. Strong seasonal winds moved enormous amounts of sand across these regions. Fossil dunes preserved in rock show that these ancient deserts remained active for extremely long periods. Life did not disappear from prehistoric deserts. Many organisms adapted successfully to dry environments. Small reptiles, insects, hardy plants, and microorganisms developed ways to survive with limited water. Temporary streams after rare rainfall events supported bursts of biological activity before dry conditions returned. Rare heavy rainstorms occasionally interrupted long droughts. Dry river channels suddenly filled with fast-moving water that carried rocks, sand and mud across the landscape. Flash floods reshaped valleys, deposited fresh sediments, and briefly filled lakes before evaporation once again reduced water supplies. Salt flats became common where lakes completely dried out. As water disappeared, dissolved minerals remained behind, forming bright layers across the ground. Repeated cycles of flooding and evaporation built thick deposits that later hardened into rock. These evaporate layers remain among the clearest signs of ancient drought. The color of many desert rocks reflects the dry conditions under which they formed. Red, orange, and brown colors often developed because iron minerals reacted with oxygen in dry environments. These colorful rocks provide additional evidence that many prehistoric regions experienced prolonged exposure to air and limited water. Some prehistoric deserts experienced large differences between daytime and nighttime temperatures. Clear skies allowed strong heating during the day and rapid cooling after sunset. These temperature changes affected rocks by causing repeated expansion during the day and contraction at night. Over long periods, this physical weathering broke large rocks into smaller pieces. Wind polished exposed rocks by blowing sand against their surfaces. Over thousands of years, constant abrasion smoothed many rock faces. In some places, wind carved grooves and unusual shapes into exposed stone, leaving lasting evidence of persistent desert winds. Animals living in dry environments often gathered around permanent water sources. Springs fed by underground water became important centers of life. Fossil concentrations found near ancient springs show that many different species visited these locations regularly. Such areas supported plants, insects, reptiles, amphibians, where water remained available and larger animals searching for food and drinking water. The spread of deserts influenced the evolution of many groups of plants and animals. Natural selection favored individuals that used water efficiently, tolerated high temperatures, or survived long periods without rainfall. Over many generations, these characteristics became more common in populations living under dry conditions. Seeds became especially important for many plants living in drought-prone regions. Tough protective coverings allowed seeds to survive long dry periods before rain returned. When moisture finally reached the soil, rapid germination allowed plants to complete much of their growth before another dry season arrived. Roots also became more specialized. Some plants developed very deep root systems that reached underground moisture, while others spread wide networks of shallow roots that quickly absorbed rainwater before it evaporated. These different strategies helped plants survive in regions where rainfall remained unpredictable. Animal behavior also changed in response to drought. Some species became more active during cooler nighttime hours. Others rested in shaded areas during the hottest parts of the day. Burrowing became an effective way to escape surface heat and conserve water. These behaviors improved survival without requiring major physical changes. Large droughts sometimes occurred alongside periods of widespread extinction. Environmental stress reduced available food, fresh water, and suitable habitats. Species already struggling with other challenges became even more vulnerable when drought persisted. Although drought alone did not always cause extinctions, it often increased the pressure on ecosystems already affected by volcanic activity, climate change, or other environmental disturbances. The fossil record preserves evidence of changing ecosystems before, during, and after major droughts. Layers rich in plant fossils may suddenly become much less diverse. River deposits may give way to wind-blown desert sands. Lake sediments may be replaced by thick salt deposits. These changes recorded in rocks allow scientists to reconstruct ancient environmental history with increasing detail. Modern deserts provide useful information about the processes that shaped prehistoric deserts. Wind erosion, dune formation, evaporation, flash flooding, and soil development continue to operate today. By studying these natural processes, scientists gain a better understanding of how similar events shaped ancient landscapes over millions of years. Many regions that are now green and fertile were once covered by deserts. Likewise, some places that are deserts today were once covered by forests, lakes, and rivers. The movement of continents, changing climates, and shifting rainfall patterns have repeatedly transformed Earth's landscapes throughout geological history. These long-term natural changes continue to influence the distribution of deserts, grasslands, forests, rivers, and ecosystems across the planet. The Earth has experienced powerful storms for hundreds of millions of years. During the Paleozoic and Mesozoic eras, the planet passed through many different climates, changing sea levels, shifting continents, and changing ocean conditions. These changes affected the movement of air and water across the planet. Although no human beings were alive to see these storms, scientists have learned a great deal about the ancient world. By studying rocks, fossils, sediments, and the chemical signs left behind in ancient layers of the Earth. These discoveries help researchers understand that very large hurricanes probably formed over the warm oceans of these distant ages. While the exact size and strength of each storm can never be known, the conditions during many parts of the Paleozoic and Mesozoic eras were suitable for the development of very powerful tropical cyclones. A hurricane is a large rotating storm that forms over warm ocean water. It gains its energy from the heat stored in the sea. Warm water causes large amounts of water to evaporate into the air. As this moist air rises, it cools and forms clouds. Heat is released during the formation of these clouds, and this released heat helps the storm continue growing. If the surrounding atmosphere is favorable, the storm becomes stronger as more warm and moist air moves into it. Strong winds begin to circle around the center of the storm, and heavy rain falls over large areas. These basic processes have existed for a very long time because they depend on the natural movement of air, water, and heat, all of which have been present on Earth for billions of years. The Paleozoic era began about 541 million years ago and ended about 252 million years ago. During this long period, the continents slowly moved across the planet as the plates beneath them shifted. Vast oceans covered much of the Earth, and many shallow seas spread across the continents. Marine life became rich and varied. Fish appeared and became more diverse. Plants spread across the land, followed by forests that covered large regions. Insects grew in number, and later the first reptiles appeared. Throughout this long history, the atmosphere, oceans, and climate continued to change. These changing conditions affected the development of storms over both the oceans and the land. At the beginning of the Paleozoic era, much of the Earth's land was broken into separate continents. Large oceans separated these landmasses. Many regions were covered by shallow tropical seas. Water in these shallow seas often became warm because sunlight easily heated the upper layers. Warm tropical waters could provide the energy needed for tropical storms. As moist air rose above these warm waters, clouds formed, rainfall increased, and rotating storm systems could develop whenever the atmosphere became unstable. The position of the continents played an important part in shaping ancient weather. Continents located near the equator received stronger sunlight throughout the year. Their nearby oceans usually remained warm for long periods. Warm water increased evaporation, filling the lower atmosphere with moisture. This moisture supplied the fuel needed for large tropical storms. Some ancient coastlines stretched for thousands of kilometers, providing long areas where hurricanes could travel before reaching land. During the Ordovician period, sea levels remained high for much of the time. Large areas of the continents lay beneath shallow seas. Marine organisms flourished in these waters. The warm oceans supported active evaporation. Air rising from the sea carried great amounts of moisture into the atmosphere. Seasonal changes in wind direction may have helped organize some storms into rotating systems. Even though scientists cannot observe these storms directly, climate models suggest that tropical cyclones were likely present whenever warm oceans and favorable winds existed together. Later in the Paleozoic era, the Silurian period brought warmer conditions after earlier episodes of widespread glaciation. Sea levels changed as ice melted and oceans expanded once again. Tropical regions remained warm, allowing evaporation to continue at high rates. Moist air frequently rose into the atmosphere. Thunderstorms developed over both the oceans and nearby land. Groups of thunderstorms sometimes joined together, increasing the chance that large rotating storms formed above warm seas. The Devonian period is often remembered as the age of fishes because fish became highly diverse in the oceans, rivers, and lakes. Large reef systems developed in many shallow seas. Forests spread across the land, changing the movement of water between the ground and the atmosphere. Trees released water vapor through their leaves, adding moisture to the air. Rivers carried fresh water into the oceans, affecting coastal conditions. The interaction between warm seas, moist air, and changing wind patterns probably supported powerful tropical storms during many parts of this period. As forests became larger, they also influenced rainfall. Moisture released from vegetation entered the atmosphere and later returned as rain. This natural cycle increased humidity over some regions. Along coastlines, humid air flowing over warm ocean water may have strengthened developing storms. Heavy rainfall associated with these storms could have caused flooding in low-lying coastal environments. Rivers might have overflowed, carrying mud, sand, and plant material into shallow seas. The Carboniferous period was marked by widespread forests, extensive swamps, and high levels of oxygen in the atmosphere. Warm tropical regions supported thick vegetation. large river systems carried sediment into coastal waters. At different times, glaciers also existed in southern parts of the planet, creating strong differences between climate zones. Tropical oceans remained warm enough to support hurricanes in many regions. Storms moving inland could have produced heavy rainfall over forests and swamps, changing river channels and depositing fresh layers of sediment. The atmosphere during the Carboniferous period differed from that of today in several ways. Oxygen levels were higher than modern values, while carbon dioxide changed over time. These differences affected plant growth and atmospheric circulation. Although hurricanes receive their energy mainly from warm ocean water, rather than oxygen levels, the overall structure of the atmosphere still influenced wind patterns and storm development. Strong seasonal winds may have guided tropical cyclones across large ocean basins before they reached land. Toward the end of the Paleozoic era, the continents gradually joined together to form the supercontinent known as Pangaea. This enormous landmass stretched across a large part of the planet. A single vast ocean surrounded much of it. The formation of this supercontinent changed global wind patterns, rainfall, ocean currents, and seasonal weather. Coastal areas remained favorable for hurricanes because they bordered warm tropical waters. Interior regions located far from the oceans often became much drier, since moist ocean air had difficulty reaching deep inland. As Pangaea continued to grow, some coastlines became extremely long. Hurricanes traveling along these warm coastal waters could remain over the ocean for extended periods before making landfall. Since tropical cyclones weaken after moving over land, spending more time over warm water allowed them to continue drawing energy from the sea. This may have helped some storms reach great strength before eventually crossing coastal regions. The Permian period marked the final part of the Paleozoic era. Much of the world's land was united within Pangaea. The interior of the supercontinent experienced dry conditions because it lay far from the oceans. Coastal regions remained much wetter. Tropical seas still supplied moisture to the atmosphere. Hurricanes likely developed over these waters during favorable seasons. When these storms reached land, they brought heavy rain, strong winds, and flooding to coastal plains. Ancient hurricanes probably affected many living organisms. Strong waves disturbed shallow marine habitats where shellfish, corals, and other sea life lived. Heavy rain changed the amount of fresh water flowing into coastal seas. Sediment carried by rivers covered parts of the sea floor. Some animals survived these changes, while others experienced difficult conditions. Storms also damaged coastal forests by breaking branches, uprooting trees, and washing soil away from river banks. Scientists study storm deposits preserved inside ancient rock layers. Large storms sometimes carry sand from beaches into nearby lagoons or shallow seas. They may also move broken shells, mud, and plant material into new locations. These storm deposits can remain buried for millions of years before becoming solid rock. Geologists examine these layers to identify signs of ancient hurricanes. The size of sediment grains, the arrangement of rock layers, and the types of fossils found together provide important clues about powerful storms that happened in the distant past. The end of the Permian period was marked by the greatest mass extinction known in Earth's history. Massive volcanic eruptions released enormous amounts of gases into the atmosphere. Temperatures changed, ocean chemistry was disturbed, and many living organisms disappeared. Climate systems became unstable. Although hurricanes were not responsible for this extinction, changing temperatures and altered ocean conditions probably affected where tropical storms could form and how often they developed. The Mesozoic era began after this extinction and lasted until about 66 million years ago. It included the Triassic, Jurassic, and Cretaceous periods. During these millions of years, dinosaurs became the dominant land animals. The first mammals remained small. Flying reptiles and later birds moved through the skies. Large marine reptiles lived in the oceans. Throughout this era, Earth's climate was often warmer than today, and sea levels frequently remained high. Warm oceans covered broad areas, creating conditions favorable for powerful hurricanes. The age of the dinosaurs lasted for a very long time in Earth's history. It began during the Triassic period, continued through the Jurassic period, and ended during the Cretaceous period. During these many millions of years, the climate of Earth was often much warmer than it is today. Although the weather changed from place to place and from one period to another, many parts of the world experienced long stretches of very high temperatures. These hot conditions created powerful heat waves that affected the land, the oceans, the atmosphere, plants, and animals. Scientists have learned about these ancient heat waves by studying rocks, fossil plants, fossil animals, ancient soils, and chemical traces preserved in sediments. These sources provide important information about the climate that existed when dinosaurs lived across much of the planet. At the beginning of the age of the dinosaurs, Earth was still recovering from the great extinction that ended the Permian period. Much of the land was joined together as the giant supercontinent called Pangaea. This enormous landmass stretched across a large part of the planet. Because of its great size, many areas were located very far from the cooling influence of the oceans. Regions deep inside the continent often became extremely hot during the daytime. The ground absorbed large amounts of heat from the sun and released it slowly. This caused temperatures to remain high for long periods. Heat waves became more common because there was little moisture to cool the air in many inland regions. The atmosphere during much of the dinosaur age also contained much higher amounts of carbon dioxide than today. Carbon dioxide is a gas that traps heat in the atmosphere. Large volcanic eruptions released huge amounts of this gas over very long periods. These eruptions did not happen only once. Many continued for thousands or even millions of years. As more carbon dioxide entered the atmosphere, Earth became warmer. Higher temperatures increased the likelihood of long-lasting heat waves across many parts of the world. The sun provided the energy that warmed Earth's surface every day. During periods when the atmosphere already contained high amounts of heat-trapping gases, even normal sunlight produced stronger heating than would occur under cooler conditions. Land surfaces became hotter during the daytime, especially in dry regions where there was little water to absorb and release heat slowly. Bare ground, rocky landscapes, and sandy areas warmed quickly under direct sunlight. During heat waves, these places could become extremely hot. Many parts of Pangaea had very dry climates. Rain did not fall regularly in every region. Without frequent rainfall, the soil lost much of its moisture. Dry soil heats faster than wet soil, because less energy is used to evaporate water. As the ground became drier, heat waves became even stronger. The lack of moisture also reduced cloud formation. Fewer clouds allowed more sunlight to reach the surface during the day, increasing temperatures further. Heat waves during the dinosaur age may have lasted for many days, weeks, or even longer in some regions. High-pressure weather systems could remain over large areas for extended periods. Under these conditions, air slowly sank toward the ground. Sinking air becomes warmer and suppresses cloud formation. Without clouds, sunshine remained strong from morning until evening. Rain became less likely, allowing the heat wave to continue. The nights during these heat waves often remained warm. Normally, temperatures fall after sunset because the ground releases heat into the atmosphere and then into space. However, when the atmosphere contains large amounts of carbon dioxide and water vapor, some of this heat remains trapped near the surface. Warm nights reduce the opportunity for living things to recover from the intense daytime heat. Plants continue losing water, while animals remain under heat stress throughout the night. Large deserts developed across parts of Pangaea. Wind carried sand across wide areas, creating dunes that stretched for great distances. These desert regions experienced some of the hottest conditions on Earth during the dinosaur age. Daytime temperatures may have risen to levels that challenged the survival of many living organisms. Only species that could tolerate extreme heat or avoid it through special behaviors were able to live successfully in these environments. Even areas that were not deserts experienced severe heat waves. Grass had not yet evolved during much of the dinosaur age, so landscapes were covered by other kinds of plants, such as ferns, horsetails, cycads, conifers, seed ferns, ginkgos, and many early flowering plants during the later part of the Cretaceous. Different plant communities responded to heat in different ways. Some had thick leaves that reduced water loss. Others developed deep root systems that reached underground moisture. These features helped plants survive long periods of hot weather. When heat waves continued without enough rainfall, many streams became smaller. Small ponds dried up completely. Rivers that depended mainly on seasonal rain carried less water. Wetlands shrank, reducing the habitat available for many animals. Fish, amphibians, reptiles, insects, and plants that depended on fresh water experienced increasing pressure as water supplies decreased. Dinosaurs needed water just as modern animals do. Large plant-eating dinosaurs probably spent much of their time searching for food and reliable water sources. During prolonged heat waves, they may have traveled longer distances between feeding areas and rivers. Fossil evidence suggests that some dinosaur species migrated across broad regions. Seasonal movement may have helped them avoid the hottest and driest conditions. Large meat-eating dinosaurs also faced difficulties during extreme heat. Hunting required energy, and moving under very hot conditions increased the risk of overheating. Predators may have become more active during the cooler parts of the day, such as early morning or late evening. They may have rested during the hottest hours when direct sunlight was strongest. Smaller dinosaurs had certain advantages during heat waves. Many could seek shelter beneath vegetation, inside burrows, or among rocks. Some early mammals living alongside the dinosaurs were small and probably spent much of their time underground, where temperatures remained more stable than at the surface. Burrows protected animals from intense daytime heat while also reducing water loss. Heat affected dinosaur eggs as well. Eggs buried in sand or soil depended on suitable temperatures for proper development. If the ground became too hot during long heat waves, developing embryos could experience stress. Some dinosaur species may have selected nesting areas with shade, vegetation, or moist soil that remained cooler than exposed ground. Volcanic activity played an important role in creating many warm periods during the dinosaur age. Massive volcanic provinces formed when enormous amounts of lava erupted across wide regions. These eruptions released carbon dioxide, sulfur gases, water vapor, and other substances into the atmosphere. Although volcanic dust sometimes caused temporary cooling by blocking sunlight, the long-term increase in carbon dioxide produced stronger warming that lasted much longer than the brief cooling episodes. During the Triassic period, volcanic activity associated with the breakup of Pangaea released huge amounts of gases into the atmosphere. As continents slowly began separating, cracks formed in Earth's crust. Lava poured onto the surface through these openings. Over long periods, this volcanic activity contributed to higher global temperatures. Heat waves became more frequent as the climate warmed. During the Jurassic period, Earth generally remained warm. Forests spread across many regions, especially where rainfall was abundant. However, warm climates did not prevent heat waves from developing. Even forested areas experienced periods of unusually high temperatures. Trees lost water more rapidly through their leaves during these events. If rainfall remained low, some forests became stressed and growth slowed. Conifer forests covered large parts of the land during the Jurassic. These trees had narrow leaves that helped reduce water loss. Their structure allowed many species to survive warm climates. Even so, prolonged heat waves could damage young trees and seedlings, making it difficult for forests to recover after severe drought. During the Cretaceous period, Earth experienced some of the warmest climates in its history. Sea levels were much higher because there was little permanent ice at the poles. Warm oceans added moisture to the atmosphere, increasing humidity in many coastal regions. Heat waves in humid climates can be especially difficult because sweat or other cooling methods become less effective when the air already contains large amounts of moisture. The polar regions during much of the dinosaur age were much warmer than they are today. Forests even grew at high latitudes, where ice sheets are found today. Although these regions experienced months of darkness during winter because of Earth's tilt, summer temperatures were warm enough to support diverse ecosystems. Heat waves could also occur in these northern and southern forests during the long summer daylight. Scientists study tiny bubbles trapped inside ancient minerals to estimate temperatures from the distant past. They also examine oxygen isotopes preserved in shells and other fossils. Different ratios of oxygen isotopes provide clues about ancient temperatures and rainfall. These scientific methods show that many intervals during the dinosaur age were much warmer than the modern world. Fossil leaves also provide evidence of ancient heat. The shapes, sizes, and tiny openings called stomata reveal information about the atmosphere and climate. Plants growing under high carbon dioxide conditions often develop fewer stomata because they do not need as many openings to obtain carbon dioxide. This evidence supports the idea that greenhouse gas levels were much higher during many parts of the dinosaur age. Ancient soils preserve signs of repeated drying and heating. Certain minerals form only under hot conditions. Cracks in fossil soils indicate cycles of drying after water evaporated. Layers of salt left behind as lakes dried provide additional evidence that prolonged hot weather affected many regions. The oceans also responded to heat waves. Warm surface water absorbed less oxygen than cooler water. Marine animals that depended on oxygen-rich water sometimes experienced stressful conditions during periods of exceptional warmth. In shallow seas, high temperatures increased evaporation, making seawater saltier in some places. Changes in temperature and salinity affected marine ecosystems. Marine reptiles such as ichthyosaurs, plesiosaurs and mosasaurs lived in ancient seas during different parts of the dinosaur age. Although they lived in water, they were not protected from rising temperatures. Extremely warm surface waters could force some species to seek cooler, deeper water, where conditions remained more suitable. Coral reefs existed in many warm, shallow seas. Reef-building organisms depended on stable environmental conditions. Heat waves lasting for long periods could stress reef communities, slowing growth or causing local damage. Fossil reefs sometimes record interruptions in growth that may be linked to unusually warm conditions. Many insects also experience the effects of heat waves. Some species reproduced more quickly under warm conditions, while others struggled if plants dried out. insects formed an important part of food chains. Changes in insect populations affected reptiles, early birds, mammals, amphibians, and many dinosaurs that fed on them. Flowering plants appeared during the later part of the Cretaceous period. Their spread changed many ecosystems. Heat waves influenced flowering times, seed production, and pollination. Some plants survived by completing their life cycles before the hottest part of the year arrived. Others produced seeds capable of remaining dormant until rainfall returned. Wildfires probably became more common during periods of prolonged heat and drought. Dry vegetation burns more easily than moist plants. Fossil charcoal preserved in ancient rocks shows that fires occurred throughout much of Earth's history, including the age of the dinosaurs. Lightning from thunderstorms could ignite dry forests and grass-like vegetation where suitable fuel existed. Volcanic eruptions also started fires by producing hot lava and burning ash. After wildfires, landscapes often changed significantly. Some plants were destroyed, while others recovered quickly from surviving roots or seeds. Open spaces created by fire allowed new vegetation to grow when rainfall returned. Dinosaurs living in burned regions had to search for fresh feeding grounds while forests slowly recovered. Heat waves influenced the water cycle across the planet. Higher temperatures increased evaporation from lakes, rivers, wetlands, and oceans. More water entered the atmosphere as vapor. Some areas later received heavy rainfall when weather systems shifted, while others remained dry for extended periods. These changing conditions created alternating periods of drought and flooding. Monsoon systems probably developed across parts of Pangaea because of the enormous landmass and seasonal heating differences between land and sea. During certain seasons, moist air moved inland and brought heavy rain. During other seasons, dry air dominated. Heat waves were especially severe when dry seasons lasted longer than usual. Mountain ranges influenced local temperatures by affecting wind patterns and rainfall. Air rising over mountains cooled and produced rain on one side. Descending air on the opposite side became warmer and drier. These rain shadow regions often experienced hotter conditions and more frequent heat waves than nearby coastal areas. Different dinosaur species developed body structures that may have helped regulate heat. Long necks increased the body's surface area. Large air sacs connected to the lungs improved breathing and may have assisted with cooling. Some dinosaurs possessed feathers that provided insulation, but may also have protected the skin from direct sunlight. Skin color may have varied among species, influencing how much sunlight was absorbed, although direct evidence remains limited. Very large dinosaurs had special challenges during heat waves. Their enormous bodies stored heat for long periods. Once warmed, they cooled only slowly. Access to shade, water, and cooler nighttime temperatures became important for maintaining safe body temperatures. Large plant-eating dinosaurs may have rested during the hottest hours before becoming active again later in the day. Young dinosaurs were especially vulnerable because their smaller bodies lost water more quickly. They also depended on adults for protection and access to food. Extended heat waves may have reduced survival rates among hatchlings if water and vegetation became scarce. The distribution of dinosaur fossils suggests that different species occupied climates suited to their needs. Some lived mainly in humid forests, while others inhabited dry floodplains, deserts, coastal regions, or polar forests. Heat waves affected each environment differently, depending on rainfall, vegetation, and local geography. Ancient lakes preserved detailed records of changing climate. Thin layers of mud settled on lake bottoms year after year. Scientists study these layers to identify periods of drought, heavy rainfall, volcanic ash, and changing temperatures. Certain layers indicate repeated drying, showing that heat waves and drought sometimes occurred together. Tree rings preserved in fossil wood also provide valuable climate information. During years with favorable growing conditions, trees produced wider rings. During hot and dry years, growth slowed and rings became narrower. Long sequences of fossil tree rings helped scientists reconstruct patterns of ancient climate over many years. The atmosphere circulated heat around the planet through global wind systems. Warm air rose near the equator and moved toward higher latitudes before sinking again. Ocean currents also transported warm water across great distances. During especially warm periods, these circulation systems distributed heat into regions that today experience much cooler climates. The absence of large permanent polar ice sheets influenced global temperatures. Ice reflects sunlight back into space, helping cool the planet. Without extensive ice cover, more solar energy was absorbed by Earth's surface and oceans. This increased overall warming and supported the development of widespread heat waves. Cloud cover varied from place to place. Clouds can reduce daytime heating by reflecting sunlight, but they also trap heat during the night. The balance between these effects depended on cloud type, thickness, and location. Changes in atmospheric circulation during the dinosaur age influenced where clouds formed and how long they remained. Seasonal changes continued throughout the dinosaur age because Earth's axis remained tilted. Summer brought stronger sunlight to one hemisphere while winter affected the other. Heat waves usually developed during the warmest parts of the year when sunlight was most intense. Some years may have experienced longer or stronger heat waves because of changing weather patterns. Changes in Earth's orbit also affected climate over very long timescales. Small variations in the shape of Earth's orbit, the angle of its axis, and the direction of its tilt altered how sunlight reached different parts of the planet. These slow changes influenced temperatures, rainfall, and the likelihood of prolonged warm periods over thousands of years. Many dinosaur footprints are preserved in ancient mud that later hardened into rock. Some trackways indicate that animals gathered near rivers, lakes, and wetlands. During heat waves, these water sources became important meeting places for many different species. As water became scarce, more animals concentrated in smaller areas. Competition for water increased during severe drought associated with heat waves. Plant-eating dinosaurs needed large amounts of vegetation, which became less available as plants dried. Meat-eating dinosaurs depended on healthy populations of prey. Stress affecting one group eventually influenced many others within the ecosystem. Some rivers during the dinosaur age were fed by distant mountain rainfall rather than local storms. Even if nearby regions experienced heat waves, rivers supplied by wetter highlands sometimes continued flowing. These rivers created green corridors, where plants and animals could survive during dry periods. The chemistry of ancient rocks records repeated episodes of evaporation. Minerals such as gypsum and halite formed when water bodies became shallow and evaporated under hot conditions. Their presence in sedimentary rocks indicates that high temperatures and dry climates affected many regions during different parts of the dinosaur age. Scientists use climate models to study how Earth may have functioned during the age of the dinosaurs. These computer simulations combine information about ancient geography, atmospheric composition, ocean circulation, sunlight, and volcanic activity. Many models produce widespread warm climates with frequent heat waves, especially across the interiors of large continents. Heat waves also affected microorganisms living in soils, lakes, and oceans. Bacteria and other microscopic organisms responded quickly to changing temperatures. Their activity influenced nutrient cycling, decomposition, and the availability of essential elements needed by plants and animals. Warm temperatures increased the rate of evaporation from dinosaur skin, scales, feathers, and eggs. Animals that could reduce water loss had better chances of surviving prolonged dry periods. Behavioral changes, such as resting in shade, remaining near water, or becoming active during cooler hours, also improved survival. Some dinosaur species lived close to coastlines where sea breezes helped moderate temperatures. Air moving from the ocean toward land often reduced daytime heating. Inland regions located far from the sea lacked this natural cooling and experienced stronger heat waves. The breakup of Pangaea gradually created new coastlines. As continents separated, marine influences reached areas that had once been far inland. Over millions of years, these geographic changes altered local climates, rainfall patterns, and the distribution of heat waves. The fossil record shows that climates changed repeatedly throughout the dinosaur age. Warm intervals alternated with somewhat cooler intervals, although overall temperatures remained higher than those of the modern world. For much of this time, heat waves appeared under different climate conditions, but were especially intense during periods of high atmospheric carbon dioxide and widespread drought. Scientists continue discovering new fossil sites that improve our understanding of ancient climates. Each new discovery provides additional information about temperatures, rainfall, vegetation, animal behavior, and environmental change. Rocks from different continents reveal that heat waves were not limited to one part of the world. Evidence appears across ancient North America, South America, Europe, Africa, Asia, Antarctica, and Australia, showing that prolonged periods of extreme heat affected many dinosaur ecosystems at different times throughout this long chapter of Earth's history. Earth has experienced many different climate conditions during its very long history. Some of the most powerful weather events happened when the continents were joined together into huge landmasses called supercontinents. These giant landmasses changed the movement of air, water, heat, and moisture across the planet. Because of their enormous size, they created weather conditions that were very different from those found on Earth today. Among the most important of these conditions were long-lasting thunderstorms that developed over large areas and continued for long periods. These storms were part of the natural climate system and played an important role in shaping the land, affecting rivers, changing forests, and influencing the lives of the plants and animals that lived during those ancient times. A supercontinent formed when many smaller continents slowly moved together because of the movement of Earth's tectonic plates. This process took millions of years. After the continents came together, they formed one giant landmass surrounded by large oceans. Famous supercontinents included Rodinia, Pannotia, Pangaea, and even older landmasses that existed during the earliest parts of Earth's history. Each supercontinent existed under different climate conditions, but they all had one important feature. Their great size changed how weather developed across the land. The center of a supercontinent often lay very far from the sea. Coastal regions received moisture from nearby oceans, but the interior could become very dry because moist air lost much of its water before reaching those distant places. At the same time, many other regions of the supercontinent remained warm and humid because of nearby seas, large lakes, wetlands, and thick forests. These moist regions became ideal places for frequent thunderstorms to develop. Thunderstorms form when warm, moist air rises into the atmosphere. As the rising air moves higher, it cools. water vapor changes into tiny droplets that form clouds. During this process, heat is released into the atmosphere. This released heat allows the rising air to continue climbing even higher. As more warm air rises from below, the cloud grows taller and taller until it becomes a thunderstorm cloud. Inside these clouds, water droplets, ice crystals, and hail move rapidly because of powerful upward and downward air currents. These movements create electrical charges that eventually produce lightning. Ancient supercontinents often experienced very warm surface temperatures. The strong sunlight heated the land during the day, especially in tropical and subtropical regions. Warm ground heated the air above it. The heated air became lighter and began to rise. If enough moisture was present, towering storm clouds developed. During certain seasons, these storms appeared almost every day. Some continued for many hours before slowly weakening while new storms quickly formed nearby. The enormous size of the supercontinents allowed weather systems to remain active across huge distances. Instead of affecting only one small region, thunderstorms sometimes stretched across hundreds of kilometers. Groups of storms formed long lines that slowly moved across forests, floodplains, wetlands, and shallow inland seas. One storm could weaken while another formed beside it, creating long periods of rain, lightning, strong winds, and loud thunder. Scientists study ancient climates by examining many different kinds of evidence preserved inside rocks. Layers of sediment record the action of rivers and floods. Certain minerals form only under wet or dry conditions. Fossils show which plants and animals lived in particular environments. Ancient soils preserve signs of repeated rainfall. Growth rings in fossil wood provide clues about changing seasons. Chemical elements trapped inside rocks and fossils also help scientists estimate temperatures and rainfall from long ago. These different sources of evidence suggest that some regions of ancient supercontinents experienced repeated heavy rainfall over very long periods. During the time of Pangaea, large areas lay near the equator. The tropical climate produced high temperatures throughout much of the year. Warm oceans surrounding the supercontinent supplied large amounts of moisture to the atmosphere. Winds carried this moisture inland. As the warm air continued moving over heated land, thunderstorms frequently developed during the afternoon and evening. Many parts of ancient forests remained damp because repeated rain fell over long periods. Thick vegetation released additional moisture into the air through tiny openings in leaves. This natural process increased humidity above the forests. The extra moisture made conditions even more favorable for thunderstorm development. As one storm passed, the ground remained wet, allowing more water to return to the atmosphere through evaporation after sunlight returned. Large river systems crossed many ancient supercontinents. Rivers collected rainwater from wide areas and carried it toward the sea. Heavy thunderstorms often caused rivers to overflow their banks. Floodwaters spread across nearby plains, leaving behind fresh layers of mud and sand. These flood deposits later hardened into rock. Today, geologists study these rocks to understand the ancient weather that created them. Many low-lying regions contained extensive swamps and wetlands. These places stayed wet because rainfall occurred again and again. Thick plant growth covered much of the ground. Dead plants slowly collected beneath shallow water, where they decayed very slowly because oxygen was limited. Over millions of years, these plant remains formed thick coal deposits that provide important evidence of ancient wet climates. Lightning was one of the most common features of these thunderstorms. Inside the storm clouds, collisions between ice particles separated electrical charges. Positive charges collected in one part of the cloud while negative charges gathered in another. When the electrical difference became strong enough, lightning suddenly travelled between different parts of the cloud or between the cloud and the ground. Each lightning strike briefly heated the surrounding air to extremely high temperatures. The heated air expanded rapidly, producing the sound of thunder. Ancient forests probably experienced frequent lightning strikes. Some strikes started natural fires, especially during seasons when rainfall became less frequent or after strong winds dried vegetation. These fires burned patches of forest before heavy rains eventually stopped their spread. Fire became one of the natural processes that shaped ancient ecosystems. Some plant groups recovered quickly after fires, while others spread into newly opened areas. Thunderstorms also produced powerful winds. As rain cooled the air inside the storm, the cooler air became heavier and rushed downward. When it reached the ground, it spread outward in all directions. These sudden winds sometimes uprooted trees, broke branches, and scattered leaves across the forest floor. Fallen trees created open spaces where young plants later grew after sunlight reached the ground. Rainfall from these storms varied greatly from place to place. Some locations received steady rain for several hours. Other places experienced intense downpours within a short time. Heavy rainfall quickly filled streams and rivers. Water flowing across hills carried loose soil into valleys. Rocks slowly wore away through erosion. Sediments traveled downstream before settling in lakes, floodplains, river deltas, and shallow seas. Mountain ranges influenced where thunderstorms formed. When moist air reached mountains, it rose along the slopes. Rising air cooled and formed clouds. Rain often fell on the side facing the wind. After crossing the mountains, the air became much drier, creating different climate conditions beyond the peaks. This process affected rainfall patterns across large parts of ancient supercontinents. Volcanic activity also influenced weather. During certain periods of Earth's history, enormous volcanic eruptions released large amounts of gases into the atmosphere. Some gases trapped additional heat, while others formed tiny particles that reflected sunlight. Volcanoes also released water vapor. These changing atmospheric conditions affected rainfall, temperatures, and thunderstorm activity. Fresh volcanic ash settled across the landscape before later becoming part of the sedimentary record. Ancient oceans surrounding the supercontinents supplied the moisture needed for many storms. Warm ocean water evaporated continuously under strong sunlight. Winds carried this water vapor over land. Seasonal wind patterns sometimes strengthened moisture transport, allowing thunderstorms to develop farther inland than usual. During especially warm periods, evaporation increased, providing even more moisture for storm formation. Some parts of the supercontinents experienced seasonal rainfall controlled by large atmospheric circulation patterns similar to monsoon systems. During warmer months, heated land drew moist air inward from surrounding oceans. As this moist air moved across the land, repeated thunderstorms developed. During cooler seasons, wind directions changed, bringing drier conditions to some regions. This yearly cycle influenced river flow, plant growth, animal movement, tidal, and soil formation. The atmosphere during different parts of Earth's history did not always contain the same amounts of oxygen and carbon dioxide found today. Higher levels of carbon dioxide often produced warmer climates. Warm air can hold more water vapor than cool air. As temperatures increased, evaporation from oceans, lakes, and wetlands also increased. The additional moisture helped support frequent thunderstorm activity across suitable regions. During the Carboniferous period, much of the land near the equator remained warm and wet. Vast swamp forests covered extensive lowlands. Frequent rainfall supported enormous plant growth. Repeated thunderstorms supplied water that maintained these wetlands. The remains of these ancient forests later formed many of the world's important coal deposits. Large insects lived in some of these humid environments. Dragonflies with very large wings flew above wetlands and rivers. Giant millipedes moved across the forest floor. Amphibians lived in ponds, streams and marshes created by regular rainfall. Reptiles gradually became more common as climates changed across different regions of the supercontinents. Dinosaurs later appeared during the age of Pangaea. Many dinosaur habitats experienced seasonal rainfall produced by repeated thunderstorms. Rivers supplied drinking water, while floodplains supported rich plant life that fed many plant-eating dinosaurs. Meat-eating dinosaurs hunted animals living within these productive environments. Storms influenced the availability of water and food throughout the changing seasons. Thunderstorms also affected smaller animals such as insects, reptiles, mammals, amphibians and birds that appeared later in Earth's history. Heavy rain created temporary pools where many animals reproduced. Wet soil allowed burrowing animals to dig more easily. Fresh plant growth after rainfall provided food for countless plant-eating species. Ancient lakes often expanded after periods of heavy rainfall. Water levels rose as rivers carried additional water into the basins. Fish populations benefited from increased water supplies. Aquatic plants spread into newly flooded areas. Fresh sediment carried by rivers buried dead plants and animals, helping preserve fossils that scientists study today. Floodplains changed constantly because of repeated thunderstorms. River channels shifted after major floods. New channels formed while older ones filled with sediment. Sandbars appeared and disappeared. Small lakes developed where rivers abandoned former channels. These changing landscapes created many different habitats that supported a wide variety of living organisms. The repeated cycle of rainfall and evaporation also influenced soil development. Rainwater slowly dissolved minerals from rocks and carried them into the soil. Plant roots absorbed many of these nutrients. Microorganisms living within the soil helped break down dead organic matter, returning nutrients for future plant growth. Over long periods, thick, fertile soils developed beneath forests and wetlands receiving regular rainfall. Chemical weathering became especially active under warm, wet conditions. Rainwater mixed with carbon dioxide from the atmosphere and soil to form a weak natural acid. This water slowly dissolved certain minerals inside rocks. Over millions of years, large amounts of rock gradually broke down into clay and other fine materials. Rivers carried these materials across the landscape. Many thunderstorms formed during the afternoon because sunlight heated the ground throughout the morning. Rising warm air became increasingly unstable until clouds developed rapidly. Towering storm clouds often reached very high into the atmosphere. After sunset, the ground cooled, reducing the energy available for storm formation. Some storms continued through the night if enough warm, moist air remained available. Ancient coastlines often experienced sea breezes that helped trigger thunderstorms. During the day, land warmed faster than the nearby ocean. Cooler ocean air moved inland beneath warmer air rising over the land. This meeting of different air masses forced warm air upward, leading to cloud formation and afternoon storms. Similar processes probably occurred along many coastlines of ancient supercontinents. Large inland lakes also influenced local weather. Water surfaces evaporated continuously, adding moisture to nearby air. Winds carried this moisture across surrounding land, where thunderstorms sometimes formed more easily than in distant, dry regions. These lakes acted as important local sources of atmospheric moisture. Strong upper-level winds affected the movement and organization of thunderstorms. When winds changed direction with height, storms often lasted longer because rain fell away from the rising warm air feeding the storm. Under favorable conditions, very powerful thunderstorms developed with intense lightning, hail, damaging winds, and heavy rainfall. Some ancient storms probably produced hailstones. Inside powerful storm clouds, ice particles repeatedly moved upward and downward through freezing layers of the atmosphere. Each trip added another layer of ice. Eventually, the hailstones became too heavy for rising air to support. They fell to the ground together with heavy rain. Although direct evidence of ancient hail is difficult to preserve, atmospheric conditions capable of producing hail likely existed many times throughout Earth's history. Thunderstorms also played an important part in the global water cycle. Water evaporated from oceans, lakes, rivers, wetlands, and moist soil. Winds transported water vapor through the atmosphere. Clouds formed as air cooled. Rain returned water to the land, where it flowed through rivers back toward the sea before evaporating once again. This continuous movement of water helped maintain life across ancient supercontinents. Cloud cover produced by repeated thunderstorms influenced temperatures. Thick clouds reduced the amount of sunlight reaching the surface during the day. Rain cooled the ground. At night, clouds slowed the escape of heat into space. These changing conditions affected daily temperature patterns experienced by plants and animals. Many ancient plant groups depended on regular rainfall. Ferns, horsetails, club mosses, seed ferns, cycads, conifers, and many other plants required water for growth. Some reproduced best under moist conditions. Frequent thunderstorms kept soils wet enough for seeds, spores, and young plants to survive. Dense vegetation then released more moisture into the atmosphere, helping maintain humid conditions. Animal behavior also depended on rainfall patterns. Many species gathered near rivers and lakes during dry seasons. After thunderstorms filled ponds and streams, animals spread into wider areas. Fresh vegetation attracted grazing animals, while predators followed their prey. Wet conditions also increased the activity of insects that served as food for many other animals. Scientists continue discovering new evidence about ancient climates through careful study of rocks, fossils, minerals, and chemical signatures preserved across every continent. Computer climate models also help researchers understand how ancient supercontinents affected atmospheric circulation. These models use information about ancient geography, mountain ranges, oceans, vegetation, and atmospheric composition to estimate rainfall and storm activity across different regions. Research suggests that some parts of supercontinents experienced repeated cycles of drought, followed by periods of very heavy rainfall. Dry soil sometimes absorbed little water during sudden downpours. Instead, much of the rain flowed across the surface into streams and rivers, increasing the danger of flooding. Sediment carried by these floods buried plants and animals, preserving many fossils found today. The movement of tectonic plates slowly changed the positions of continents over millions of years. As supercontinents formed and later broke apart, coastlines shifted, mountains rose, oceans opened, and climates changed. Areas that once experienced frequent thunderstorms sometimes became dry deserts, while formerly dry regions later became humid forests. These gradual geological changes continuously reshaped Earth's weather systems. Evidence preserved in ancient river deposits often shows repeated layers of sand, mud, and gravel. Each layer records separate flooding events caused by heavy rainfall. Some flood deposits extend across wide regions, indicating that storms affected large drainage systems at the same time. Careful examination of these rocks allows scientists to reconstruct ancient rainfall patterns with increasing accuracy. Many minerals found in ancient soils reveal repeated wetting and drying. Certain clay minerals develop only when enough rainfall is available over long periods. Iron-rich minerals change color depending on the amount of oxygen and water present during soil formation. These features provide additional clues about ancient thunderstorm activity. The electrical activity produced by countless lightning strikes also influenced the natural environment. Lightning can break apart nitrogen molecules in the atmosphere, allowing nitrogen compounds to reach the ground through rainfall. These compounds became valuable nutrients that supported plant growth. Natural nitrogen fixation by lightning has operated throughout Earth's history. Some storms developed where warm tropical air met cooler air, moving from higher latitudes. These boundaries forced warm air upward, producing widespread cloud formation and heavy rainfall. Seasonal changes in atmospheric circulation caused these storm-producing zones to move across different parts of these supercontinents during the year. Even after one thunderstorm ended, the atmosphere often remained unstable. Wet ground increased evaporation as sunlight returned. Warm temperatures quickly heated the moist surface again. Rising humid air formed new clouds, beginning another cycle of thunderstorm development. This repeated process allowed active weather to continue day after day across favorable regions. Ancient ecosystems adapted to these repeating weather patterns over millions of years. Plants developed life cycles suited to seasonal rainfall. Animals adjusted breeding, feeding, and migration according to changing water availability. Rivers, lakes, wetlands, and forests expanded or contracted depending on rainfall, received from countless thunderstorms that crossed the giant supercontinents throughout Earth's long geological history.